Okay, so intuitively we explain gradient boosting based on a regression problem because it's easier to grasp intuitively than the classification option. If you're interested in the math of the classification option, you can see that YouTube on StatQuest Gradient Boost Part 4. The thinking behind is the same as for regression. Just the math is a bit more complex because you're dealing with logs. So the main difference is in the cost function. Here we use the squared error between the prediction and the true value, whereas in classification we will work with the log loss. And we've done some examples here when we talked about logistics regression. In logistics regression, we looked at minus the log of the likelihood. It's something similar. At the end, now I also want to give a comparison between gradient descent and gradient boosting. Are they the same? Well, mathematically yes, but in principle we're looking at other things. So what we do in gradient descent is fairly simple. It's the housing price exercise. So the blue line is our prediction line. Y predict is Wx plus B. And we said that the quality of the line we would measure with the sum of all these vertical red stripes here. That's basically the difference between Y predict that lies on the line and the true Y, which lies at the end of the red line here. Okay? So basically the goal of gradient descent is to choose your weights W and B in such a way that this cost is a minimum. So the cost is quadratic. I showed it in a graph and we've seen that in the very beginning. And you start with a weight W0. What you do in W0 is you calculate the derivative. And the derivative is the slope of the line tangent to where it hits the curve here. And you see this derivative is negative. So how I find the new W1? Well, the rule is W1 equals W0 minus alpha and then that derivative in W0. Alpha is the learning rate. When you choose it too small, it takes long to converge. When you choose it too big, you might oscillate between these. This derivative is negative, and with the negative sign here, minus alpha, this whole thing is positive. So W1 you find by adding something positive to W0, so you go in this direction. So here you're tweaking the weights, and the direction which you need to go is given by that derivative. Now gradient boosting, we don't deal with weights here. We deal with functions. We're in function space. That's why gradient boosting is often called gradient descent in function space. So the formula here that we derived is very similar. So your new function, f1, is f0 plus alpha and then the tree. And you could go this way and you could go this way. If you're in this point, your output we calculated is 402 is positive. You're in this point, your output will be minus 200.5. Minus 200.5. Okay? So here we have basically two graphs. We have a graph for samples 1 through 4. And we start with F0. And remember, F0 was the average of your housing prices. In our case, that was 398. So this is your starting point. And now your update, F1 is F0. And now we're in this piece here. Means alpha times minus 200.5, which is negative. Negative means you go in this direction. Yeah, this is where the arrows go. And so you slowly converge to the true y. Yeah. In the other case, we have the cost function here as well. F0 is still 398. Yeah? But in this case, it will be plus alpha something positive 402 divided by 10 is 40. So we're going to add 40 and we go in this direction. But also your goal is to be as close as possible to the y. Yeah? So basically these f's are your y predicts. F1 we could see as y predict 1. F0 is y predict 0. And y predict 0 we can actually also write by h0, and this would be h1. It's all the same thing. Yeah? So here what you do, you don't update weights or anything. You just update your function sequentially, and you move in the direction that brings your y predict as close as possible to y. Yeah? This is what you do in gradient boosting. But both are minimizing y predict, y minus y predict. Yeah? Both of them are minimizing this. Alright. Now we could say, well, here you have your tree, but where is your derivative? Well, remember, in order to get these output values, we needed to find a y predict that minimizes the cost function. We actually, to find the minimum, had to take the derivative of the cost function with respect to yp. Yeah? So here that derivative is actually embedded in the construction of your tree. Yeah? And that derivative will tell you which way to go. Yeah? Which we see here as well. Alright, that finalizes boosting. We've not discussed XGBoost yet, but we will use the library in our coding session. Just an overall summary. Lesson 11 is about decision trees. Decision trees have a variance issue. Yeah? And you can solve this by bagging. And if you apply bagging on decision trees, you have the algorithm random forest. Yeah? Strong algorithm. There's no hyperparameters to tune. Yeah, it works right out of the box. No feature scaling needed. If you have a bias issue, you do boosting. We see an AdaBoost classifier, and the last thing we saw was gradient boosting, which can be used for classification and regression. As we will see in the coding exercise, the gradient boosting is not that obvious. Although, I mean, it's simple code. The thing is on how you optimize or tune your parameters. Yeah. Okay, that's it. So let's move to the coding session.